Can we put the slides up?
The slides are up.
OK, so we have this little ticker. Hi, we're going to talk about fraud detection, but fraud is a broad word. Think about it as anomaly detection. So we're going to have intros, we're going to review the problem, quick overview of key technologies, and we're going to try to go fast on that, but there's a rule in the presentation, and the rule is ask as many questions as you like. If we take too long, it's your fault. But you might learn, you'll get the information you want. So interrupt at any time, ask what you need. If you feel like you don't want to ask in front of public, me and Gwen will be available for questions until whenever. We're going to talk about high-level architectures, deep dive of near real time, and putting it all together. So this is Gwen. She's a pirate. She helped me write this book, Hadoop Application Architecture.
No, he helped me write the book.
Essentially, if you're interested, it goes over every component in the Hadoop ecosystem. So like everything you can think of, and then how do all the pieces fit together. We had more reviewers than any other book because we covered everything in the entire ecosystem, and we needed to get at least 2 reviewers from that project to review that component. So it was exhausting. Gwen also works on Scoop, Kafka, and Flume, and she's engineering. She used to be services. I also wrote the book, I'm Not a Pirate. I have been doing Hadoop for over 5 years. I have contributed to HDFS, MapReduce, Yarn, HBase, Spark, Avro, Kite, Pig, Navigator, the Cloud Era Manager, Flume, Kafka, Scoop, Accumulo, but that was a really small one. And I'm working on a Sentry patch right now. And I've worked for about 70 companies in 8 countries. So I have a big breadth of use cases. So yeah, please ask me. So the problem here today, we're going to go over this pretty quickly, but one example fraud detection is credit card transaction where you swipe a card, you know everything, you know everything about that transaction, but you also will need information about the person making the transaction. You also need information about the vendor, and you might also need information about global statistics, right? To decide within milliseconds, right, 50 to 100 milliseconds, should I accept this charge or not for this individual, right, at this location, right? So the IKEA meatball thing. So does anybody know what IKEA is? IKEA? Okay. Does anybody know sometimes they give free lunch if you buy $100 worth of furniture? All right. You're my man, right? And you love those meatballs, right? So my brother figured out how to rig the system. Totally legit. And what he realized was he could eat over $100 worth of food, right? So even though he was following all the rules, the company was losing money, right? Same thing with a coupon. I worked with a company that was selling computers, and they had set out a variety of coupons. And someone on the internet found out that if you combined certain coupons together, you could get a laptop for $100. This was totally legit. And real-time processing was like, oh, this is a valid transaction, but the company was bleeding money. And at the end, had to embarrassingly return cancel all those orders. So there's a need for something even smarter than near real time, something that's looking at a global level to recognize, man, a lot of people are coming in, recognize threats at a global level and adjust or shut off the current rules because they're not adequate, right? Game strategies, so games, when I started working in the gaming industry, I've noticed that they have all the fraud characteristics of a bank. They even have money laundering situations, if you can believe it. So gaming industry also has very similar things. Healthcare, what was the healthcare one?
Basically, people may do things like doctor shopping. So they have their favorite drugs. They want to get their supply of Vicodin or whatever ADHD drugs are really hot on the market. They just go around until they find enough doctors that will prescribe enough things, no question asked. Again, it's something like every transaction is legit. The doctor prescribed it. You go to the pharmacy. You fill it. You need a global view to see that, hey, this doctor is prescribing every single Vicodin prescription in the entire county.
We can see it here. We can see the screen down here, and I'm looking over there. All right. So how are we going to solve this? So my uncle is one of these weird people that was smart enough to figure out the bond system at the age of 20 and retired at 25, and now he studies neuroscience for fun. And I had a conversation once with him, and I was like, how does the brain detect anomalies? And what he talked about is very similar, that's in modern books about quick thought or slow thought, fast thought, is the brain kind of reacts in 3 types of modes. And I like to relate this to how we play tennis. So when we play tennis, when the ball is coming to us, we're not thinking about Shakespeare or the velocity of the ball or how it smells in spring. What happens is our muscles and our system reacts at a muscle level. We're hardly thinking at that point. We're reacting. But that's our fastest way to react. Then the next line of thought is possibly in between sets, where the ball isn't coming, we have a second to recatch our breath, and we can review what has just happened and say, oh, the opponent is using this strategy, or they changed it up, or they adjusted to something I did. How do I adjust for the next set? And then there's reflective thought. How many people have stared at a computer trying to solve a problem for hours and hours on end, and then you go for a walk and then you find the solution? Or you fall asleep and the next morning you're like, oh, that was the answer, right? And what happens in our brain is even though we step away from the problem, our subconscious thinks about the problem in the background using deeper analytics and figures it out for us and decodes the problem into pieces and makes it easier for us to solve. This is why you should only work for about 45 minutes and then take a walk. This is a very common pattern to be able to clean the brain out and just get more thought. So why do I bring these up? We're going to talk about how to build systems that do this. The evolution has done a really good job of building our brains to detect anomalies and react to environmental controls. We're not going to do much better in building a system that does similar approaches. And this is you.
This is me.
All right.
OK, so just background about some of the technologies we're going to use when we build a system, in case you're not super familiar with them. So the basic system we're building a lot of the system around is Kafka. And Kafka is, when you first look at it, it's just a queue. You write messages in, you take messages out. Why are people making such a huge deal out of a queue? Well, part of it is hype, but then you start looking at, OK, what does Kafka give over other queues? And you see that, first of all, it's very fast, as in very low latency. And at the same time, you can get very high throughput. So it's very common for it's very easy with 5-node cluster, for very cheap, to have 1.5 million transactions a second. So it scales very well to the kind of use cases we're talking about. It not just scales in terms of how many transactions you can get through. It also scales in terms of number of producers and consumers. So you can have 100,000 different consumers. You'll still, with those 5 nodes, you'll still get super good, nice performance. You add more nodes, obviously, you can do better and better. It's partitioned. It's a distributed system. It's highly available. You lose a node, nothing bad happened. No need to wake someone up in the middle of the night. It's also nice because consumers can be of different types. One of those types can be something that only wakes up once an hour and once a day, grabs data from the last day, and dumps it to HDFS for analysis. This is something you really couldn't do with things like TibCore, ActiveOMQ, or whatever else you're currently using, because they're trying to actually track the consumers and keep in memory messages that were act or not act yet. Kafka doesn't do any of it. It decided that I don't care about who read the data. I'm keeping data for X amount of time. Whether or not someone read it, it's their own problem. So it gives a bit more work to the developer at the benefit of being very, very scalable to many different use cases. So Kafka Basics. Kafka is a message queue, so you have messages. Messages are organized into topics that you can subscribe to. Producers write messages to those topics. Consumers take messages out of those topics. It runs in a cluster, and the nodes in the cluster are called brokers. The way a topic looks from the inside is that it's partitioned. So you produce data to those partitions, and each message gets an offset based on its location in the partition. Kafka, one of the basic properties is that it preserves order within a partition. So you will be reading data out in the exact same order you wrote it in. Very important when you're dealing with transactions. Yeah. Okay, each partition is basically like a log file, which is pretty much what I just described. And the way that consumers know where they are in this log is that they track down which offsets they're currently reading. As I mentioned, it's the consumer responsibility to know which message is it currently reading. Kafka arrives built in with a client that tracks messages either in Kafka itself or in Zookeeper, but you're free to write your own client and track messages in places like HDFS, MySQL, wherever you want to track offsets, you have the ability to do so. So, and the idea is that suppose that you read and then, hey, I lost data, or I want to reprocess something because I have a better algorithm, or I need to see the data from yesterday. The data is still there. You switch, you go back in offsets. You say 10 messages ago or 3 days ago, and you can get the data from scratch. And because Kafka is so scalable, you can keep a week of data. You can also store 3 years of data. It just depends on how many machines and how much storage you normally have. So as we said, the topics are partitioned, and each broker stores a large number of partitions. Each partition can also have multiple replicas. So here you see we have 3 partitions. Each partition has 3 replicas. One of the replicas is highlighted in bright orange. This is the leader. So currently, the model is that each partition has a leader. All reads and all writes go to that leader. Other partitions replicate data from the leader. So you don't have a consistency problem. Everything goes through the leader. We're actually extending Kafka a bit now, so you'll be able to read from partitions that are not currently the leader, but that's a future improvement. So the client writes data to the leader, and then it looks like the leader is pushing data to the other replicas. Actually, incorrect. The replicas are pulling data from the leader. But no matter, these are implementation details. The idea is that messages go from the leader to everything else. Now, you'd say reads and writes only go to the leader. How is it load balanced? And the way it's load balanced is that you have a lot of partitions. So each broker is the leader for some subset of the partitions, and you have a load balance system. The way consumers work is that consumers can either belong to the same consumer group or different consumer groups. So if you have consumers that belong to the same group, like over here, they basically load balance the partitions. All the consumers in that group subscribe to a topic, and each one of them is responsible to some of the partitions, which means that you basically load balance the data for that topic. You get numbers from 0 to 10, you get from 10 to 20, and so on. And there can be many partitioning strategies. If one of the consumers in the group fails, no worries, the partitions will be assigned to other consumers in the group. So it's both load balancing and high availability at the same time. Now, sometimes you actually, if 2 consumers belong to the same group, it means that they're getting different messages. But sometimes you want those to have 2 consumers reading from the same topic and actually getting the same messages, just doing different things with them. One of them may be for the real-time fast reaction system, and the other for the slightly slower reflective thought system that will do some correction to the algorithm in the background. In this case, you will have 2 different consumer groups, and they will both get all the messages. Whew, that's it with Kafka. Next to a more familiar technology, hopefully, Flume. If Kafka is so perfect, why do we even need Flume in the system? Well, it's about the things that Kafka doesn't do. Kafka doesn't get messages from anywhere. Kafka doesn't push messages to anywhere. You have to implement consumers and producers. And Kafka doesn't change the messages in any way, shape, or form. In many ways, Kafka is storage. It's a bit maybe like HDFS. Flume gives all the missing pieces. So Flume has a lot of sources that can get data from different places. So you can get data from Twitter, from log files, from web servers, from Kafka itself, for that matter, and so on. Flume has interceptors, which will become super important in a second, so I'll talk about them in a moment. It has selectors, which let you redirect data to different places. It has channels, which are basically a buffer. So while the data is going through this pipeline, we have to store it somewhere. So we have those channels as places to buffer the data. And then we're writing the data to sinks. Those things can be HDFS, HBase, Solar, a bunch of other places as well. Cassandra, I think, is pretty popular. So let's zoom in a bit about the different components. First of all, how does Kafka and Flume fit together? Well, if you already have data in Kafka, you can say, Flume, please get me the data from Kafka. That's one way to do it. That's the Kafka source. The other way is the converse. If you're getting data from Twitter or log files or web servers and you need it to end up in Kafka, well, you can just write it to Kafka and you have the Kafka sync. But the most interesting use of Kafka is actually saying, I have this source, maybe a log file or a web server. I have this target, maybe HBase or HDFS, but I want the data to get buffered in Kafka in between. So so you still have the ability to process data, to send it to different places, but the data gets sent to Kafka, which means that you have basically an infinite buffer in case HBase or HDFS went down. It means that you can have other applications read the data from Kafka. And it also means that it has very high reliability. So if one Kafka node or one Flume node, if anything goes down, you still have the data in Kafka, and other Flume nodes can read it, and and you can load balance it between different nodes. Yes?
Can I add one thing?
Of course, you don't really need it. You can talk.
One thing that is really interesting to note is now that you have this paradigm, it kind of changes what we previously thought of Flume, in that you can have the first part and you don't need the second part. So if you're just pushing to Kafka, or if you're just ingesting, you only have to use the last part. You just have to use the sync. You no longer need the entire piece. Because now it's essentially, think of it as an interface design. You can come in and out to Kafka at any of these points.
And you can opt out of anything anyway. None of those are required. You don't really need a sync. You don't really need a source. You can get things from a channel to a sync or from a source to a channel. It's very much a Lego mix and match. Last point is just a short introduction to interceptors, which we'll talk about in a lot more detail. Interceptors are a piece of code sitting between the source and the channel. And the nice thing about interceptors is that they run before the data ever hits disk. So if I'm reading from, let's say, Twitter, and say I have something sensitive and I want to hide information, I can do some field masking before writing to disk, which can be important. I will not read credit cards from Twitter, but I may read credit cards from a different source, and I have to mask it before writing to disk. Interceptors are the place to do it. You can also run data validation in there. You can make modifications. You can add timestamps. You can do a lot of fun stuff in between. And that's kind of your imagination, and your latency is the limit. And last basic technology.
OK, so, oh my goodness, we are running out of time. So I'm going to try to go really fast here. So Spark Streaming, I don't know, most of you are probably familiar with Spark Streaming, but I'll do the highlights of it. And if you need a deep dive, I'll go into it later on. This is a Spark Streaming job to do word count. All right? Well, what's sexy about this? This is a Spark job to do word count. Did you see that? Yeah, that's awesome. You don't have to learn two systems. If you know one, you can optimize one. You can do it in batch mode. Then you can switch it over to a real-time mode, right? I mean, do it in real time, like micro batches. So why micro batches? And then I'll talk about how micro batches work. Micro batches at a high level give you high throughput than event level acknowledgements. Micro batches allow you to get away with not doing double counts. And we'll see in a minute, micro batches, the way Spark Streaming does it, also allows you not to lose state within your flow. These are very hard things that some competing products don't have. Spark Streaming is extremely nice if you know how to use it correctly. So how it essentially works is it takes data from a source and it puts it into an RDD. If you know anything about Spark, RDDs are immutable. But while you're writing to them, you can continue to write to them. When you close them, they no longer can change. At the interval, the initial RDD is now shut. We now essentially are doing regular Spark operations on that RDD. We can do machine learning. We can do clustering. We can do recommendation engines. We can do joins. We can do enrichments. We can do counts. We can do moving averages, whatever your imagination wants to do. And the receiver is now pushing to the next RDD. And then you can see it's just a repetitive process on the next line. So essentially, it's micro-batching within a stream. The one caveat to this is you can keep state. So state gets stored as an RDD. So an example, you store the counts in the first batch, and you use the counts on the next batch. The big win here is double counting. If you fail while you're generating that second batch, no worries. It just starts generating it again from the previous RDDs, and then you'll have your good counts. You won't get double counts out of this procedure. Where if you're doing something like putting counts in a hash map and you're incrementing and then you fail and you have to retry, you will get double counts. Now, when you're counting tweets from Twitter and you double count, no one's going to die. But there's a lot of use cases where counts are really relevant and you need to have the right answers, right? So you want something like a micro-batch system. This is another thing, and we're going to be using this, but if you're interested, there's a project that I put together that's on Cloudera Labs, which allows Spark and Spark Streaming to fully integrate with HBase without any problems. Now, out of the box with Spark and HBase, you can do bulk reads and bulk puts. With this now, you get a connection object at any time in a map method, a for each method, and you can do anything. You can look things up, you can do check puts, you can do multiple operations. I built this because I have a client who is doing real-time graph mutations and validations on a graph structure in HBase in real time.
And one of the things it's really nice for, if you've been following SAMZA and you know how important it is to maintain a local state for your stream processing, then basically HBase is the local state for Spark streaming.
Well,
so
the Spark streaming has its own local state. That would be...
No, it's a local state that you can actually edit and work with. It's,
yes. But
yeah, the same way that SAMZA uses RockDB and LevelDB.
Yes, it's kind of like that.
Yes, Spark streaming uses HBase.
Yeah, but the important thing is you don't have to you could do local state without it.
Yeah, you could totally do local state. It's even recommended to do some local caching in addition.
Yes.
Yes, I think.
Oh, is this so me?
And this implementation is open source, it's contributed on GitHub or something?
It's on my GitHub, and actually
it's also in
we're trying to get it into... So long story, we try to get into HBase and in Spark, but both projects don't want each other in them. Okay. So right now it's on my GitHub. It's under the Apache license. And no, it's also on Cloudera Labs with the Apache license. There is talk to just make it a full-fledged Apache project to
that'll be cool.
remove any of the issues. The only deterrent of that is because I don't have enough hours in the day. But yeah, it's on GitHub. Yeah, it's super simple. Essentially, it's putting a connection object into a static location, and it's keeping that alive so that you don't have to reconnect on every iteration, right? Because that would be extremely expensive, more expensive than actually doing the operations. Am I talking about this?
Yes, you are talking about this.
All right, I'm talking about this. So we're going to be going through this in the next 17 minutes, and this essentially is the architecture that will give you those 3 lines of thought. Take pictures, yay, sexy. And feel free to ask any questions. It just means that we have to go faster on content. What's the next one? Real time. OK, where does real time fit in? Real time fits in right here. OK, so we have stuff coming in. We have Kafka putting the events in. And then we have our Flume events. And then we have HBase. So what does this look underneath the cover? So this is one implementation. And then after I show you this implementation, I'm going to say you're not going to do this. So this implementation is the simple one, where you're putting in data to Kafka. It's essentially going to Flume. Instantaneously, after we get it from Kafka, we are now running logic on it. We're running our model logic on it. We're using local data for the most part. If we need external context, like a credit card transaction, if we need data on that user, we go to local memory. Why do we go to local memory? Because it's nanoseconds, right? But there's a situation of failure, or we don't have enough memory, where we might have to go to HBase. If you configure HBase, you should be getting something like 4 to 25 milliseconds for response time from HBase. We don't want to hit HBase, but if we have to, we can still meet our requirements of a low latency time even hitting HBase.
And if you're using HBase and you get anything slower than 20 milliseconds, that's why TED exists.
If you're getting slower than that, you're doing something wrong. Give me a call. All right, but this is what you should be doing. So one of the conversations I've had with the Kafka people is essentially Storm needs Kafka, but Kafka doesn't need Storm. And this is an important thing. With HBase and Kafka, there is no really need for Storm anymore. So with Kafka, we can partition the data. Why is this relevant? If we can partition the data, then we can use local memory more. So let's just say we're doing fraud detection with credit cards, right? If we partition by the users, like a hash mod on the users. We now can predict with reasonable accuracy how much memory we need to store all the profile information of those users. And if we do this correctly, now we're only accessing HBase when we first pull up the data, when we first start the system to re-get the state. But we can have the state in our local cache at all times, right? So now we're fast. We have the latency of Kafka, and then we have the latency of getting something from a local hash map, and the computational time, and then spitting the answer back out to either Kafka or the designated system, all right?
And it's a very simple architecture. It's like something
See,
that you can imagine building yourself without Storm, without Spark streaming.
Yeah.
It's just you read data from Kafka, you do something to it, and you write it to HBase.
And that's a good point. Let's say you hate Flume. Let's say Flume is a nasty word in your company. This is not Flume specific. This is a Kafka consumer. Put your consumers in Yarn. Put your consumers in a custom MapReduce job that just always stays up. Put your
Docker,
consumers on
Kubernetes.
Docker. Put your consumers in Slider. I don't care. The point of it is, it's dirt simple, and it's dirt fast.
Sorry, that question, is that event processing, the complexity of the event processing layer will decide whether Spark streaming is a better option?
We're going to go to Spark streaming in 1 minute. This is for milliseconds. And what's going on here is we're making a decision. We're making a really good decision. But this type of architecture is not good for doing aggregations. This type of architecture is not good for doing near real-time clustering, right? This is not really good for machine learning at a global scale. This is good for fast reaction. Remember the types of thought we talked about? This is muscle memory. This is as fast as we're going to get, right? Does that answer your question?
And again, latency should be in the very low milliseconds, and the throughput should be per machine in the hundreds of thousands of events per second. Like if you're not getting 20,000 events per second per machine, again, let us know we are doing something wrong. It should support this type of throughput.
Okay, I heard we have a memory channel as in Kafka channel in the Flume framework. Why were you using local memory instead of Kafka channel?
It's local. It's in your local memory. Nothing is faster.
No, it's not a Kafka channel. There's no Kafka channel here.
No. The earlier slide in the Flume framework, we have a Kafka channel.
Yeah, but in here, we're essentially just talking about the interceptor here. And the producer could essentially be going to a Kafka channel, which somebody else will read, right? It's pretty straightforward.
This is just cache for the decision-making
The local
process.
memory is not for the channel. The local memory is for credit card users' profile information. So a common thing is when I swipe the credit card, did my last 3 zip codes or something, could I have traveled to the new zip code that I just made a purchase from without teleportation? Could I have made it there in any reasonable period of time? Right? So I need some historical information about myself.
But he's correct that we're not really. Oh, we are showing.
No, that is
yes.
the channel.
So the Kafka over there that says answer topic.
That's the channel.
Basically, the interceptor is getting a transaction, but what it's writing to the channel is yes or no.
Yes, and we're not really actually using a sync. And it could be more. So one of the things we might also be doing is banks, example, or a lot of other things, will have to actually physically record either on HBase or HDFS, not just yes or no. They'll have to record the transaction, the profile information as it was at that moment in time, and so the answer.
Maybe the reason for the decision,
Yes,
like we said no because of X, Y, Z.
So that we can go back later on and say, was that a good decision, or why did we make that decision, right? So we might need to publish that information to HDFS, and that goes to a sync or something like that. But it'll depend upon the use case. So
that's mine.
now she's going to talk about what you were talking about, more complex stuff.
Okay, so at this point, this is just rapid decision making, saying yes, no, based on available data and on an existing model. So one of the things we didn't really emphasize is that usually in order to make the decision, you need some kind of threshold that is also in memory. Something like if the distance from the previous transaction is over 200 miles, and the amount of the transaction is over $10,000, and the person is currently in Russia, we flag it as a no, maybe. No offense to any Russians here. But these things are kind of hard-coded, and they may change. So this morning, I saw a tweet from Merv Adrian from Gartner saying something like, if you're going to buy, I think it was diapers, champagne, and a razor blade at the same purchase, then you may be targeted as fraud. Well, if you're smartest like me, that's the first thing you're going to do is immediately run to the nearest Target and buy those specific items just to see what happens. And so I'm guessing that pretty much very soon afterwards, and there's a lot of smart asses in Twitter, a lot of banks will have to update this specific model to something else. So how does that going to happen? And the idea is that there will be a second system, a bit slower than the actual real-time system, getting the same data from Kafka. Remember, we talked about 2 different consumer groups. And this will run in something that can do complex events processing, like Spark streaming. And Spark streaming is basically Spark, which can do machine learning, running in a very tight loop on the data, maybe every second or every half second, getting a bunch of data, accessing HBase for state. And this will include very smart algorithms that I'm completely incapable of writing myself, that can say, oh, there is a spike in this kind of activity, not just for the specific user, but over everything that is going on in our system, we need to do a larger and smarter update. Now, suppose that our algorithm decided that we no longer flag champagne, diapers, and razor blades as an interesting event because now everyone is doing it just for kicks. So we have to somehow let our fast Flume interceptor know about this change. And there is 2 ways that this can happen. It can go to HBase and say, hey, we updated the model, and maybe our interceptors will occasionally check with HBase, hey, do I have a new model? But a better way to do it is actually write back to Kafka and have a topic just for model changes and make sure that your consumers are not just subscribed to the topic with the transactions, but also to the other topic, very small one, maybe with a single partition even, that has model updates. And now whenever they just listen to it. Most of the time there's no updates, nothing happens. Every once in a while there's an update. They get it immediately. And they say, oh, an update to the model arrived. Let's apply this those new thresholds or those new rules, store them in my local cache, and do something with them. Obviously, the new model is now stored in Kafka. And Kafka has this nice property for compaction that means that if you're storing a lot of data, well, after a while, you want to start truncating data, right? You're keeping data for a week. What do you do with data older than a week? Well, you can just throw it away, but in case of the model updates, you don't want to throw the old model away just because you had no model changes for a week. What we actually do is say, for every key, always hold the last value. So you always have the most current state. And holding the most current state is awesome, not just for models. The world in general have a state. Your machines in your cluster have a current state, and you may want to store that. Your databases that you do transactions in have a current state. That's what you usually see when you query a database table. You see the current state, not every transaction that happened to it in history. So being able to just see what is the current state of the world in a world that is constantly changing is very powerful, and Kafka gives you that as well. Anything I'm missing about microbatching?
No, that's pretty good. That's pretty good.
Cool. The rest will be way faster. So in order to do the whole microbatching smart processing thing, we need to connect Spark streaming to Kafka. When I stood here last year, everyone was like, oh, but Spark streaming in Kafka loses data, and it's horrible, and it's buggy. Well, since last year, we rewrote it 3 times, and we think that this revision is actually a good one. And it gives us exactly one processing with very high throughput. So if you use Spark 1.2 and you want to not lose data from Kafka, you can use HDFS as a write-ahead log, which is, it was just, when they added this feature, it was just physically painful to me. I mean, Kafka is a log, and then you go and add HDFS as a write-ahead log when I know that HDFS is not as efficient as a log. How can you do it? So it didn't lose data, but performance made me kind of cringy every time I thought about it. In 1.3, which is, I think, either the latest or one before the latest Spark, we made something much smarter. Remember that Spark streaming has those RDDs? Well, we store the latest offset in the RDD itself. So as long as the RDD is going through the system, you have the offset next to it. When you persist the RDD, you persist the offset with it, and that's our commit. And if you somehow lost the RDD because the machine crashed, well, those offsets, you just went away, and someone, the receiver that has to read the same partition from Kafka doesn't know that anyone read this offset, and therefore it will go and read this offset again, and no data is lost. Sorry for that being kind of hand-wavy. We don't have that much time. There is a very good blog post about it. Yeah.
Sorry, it's amazing. It's really good.
Yeah.
It essentially allows you to replay the log in case of failure, so you don't have to rewrite it down.
What?
No. In the case of failure, that whole batch is canceled. And then it resets the offset to start the batch again.
So this is genuinely idempotent, right? This is idempotent in terms of how processes emerge.
It's not fully idempotent because the producers are not idempotent.
Yes.
So whoever is reading to Kafka may accidentally write to Kafka twice.
So the way you get around that is you make your producers send with it their ID and a sequence. And then you can be with that.
Very much like TCP is doing it. TCP is idempotent because of sequence numbers.
Right? But Spark streaming by itself and this, not counting the producers, is no doubles. So you just have to get all the way to the producers now.
OK, we have 4 minutes. So I'm totally going to skip the bad input handling. You can figure out how to handle bad inputs yourself. The last piece of the puzzle is that you can also get the data directly from Kafka or through Flume from Kafka to places like HDFS and Solr, where you can apply the rest of the Hadoop ecosystem to the problem.
So one I really want to talk about, this one is so cool. I had a customer who's actually in the gaming industry. What they essentially did was bring in all their chats. So all the typing, they would go into HDFS and Solr so that analysts could identify bullying behavior in real time and not know any technical background, right? Because in the gaming industry, bullying behavior is like the worst thing for long-term subscribers. Money just goes out the door. But anyways, it's really cool stuff. Okay.
Yeah, no, I think we're good. We have 3 minutes for questions, unless you want to talk about something else.
We have to do the last one.
Oh, OK, sorry.
This is an idea of how you ingest. Your ingesters are totally different, right? They're different consumer groups, and they go at their own rate. So they're not slowing each other down. They're not slowing down the real-time processing. They're not slowing down the Spark streaming. They're in their own world. And then this is everything else we know about Hadoop, right? You can use Hive if you want to go slow. You can use Impala if you want to go fast. You can use MapReduce if you're too scared of Spark. And you can use Spark.
Don't do it.
Yeah. You can use Spark if you're actually up to date. Or you can use search. But the point of it is you can use any of these tools to now learn from your data and then feed that back into the model and update your model.
So we're here showing that you can just update the HBase, but you can really write back to Kafka and update the models through that way. We just missed it in the diagram.
So in short, we're now building a system that reacts to fraud like the human brain does. And we're using minimal, most capable, enterprise things that we have available to us right now.
It's a pretty simple architecture, something that your ops people will not kill you when you try to deploy.
Yes. It's easy to maintain, it's easy to monitor, and it's easy to scale.
Yeah, and you can really, every part of it, you can just add more of it and get better scaling.
Yep.
Like you can add more Kafkas and more Flumes and more Hadoops and more HBases, pretty much everything.
So any questions?
We don't.
Huh? Yeah, no, so Cloudera learned a long time ago that Storm was going to be end of life. And so we decided not to support it. And if you even look today, Spark has 700 commits in the last month. When I wrote the blog article last week, Storm only had 15 in the last month, but after I complained that Storm had no commits, they did 8 that one day. But Storm in general, even Twitter released last week that they're now moving on from Storm. And the reason is Storm was built a long time ago for a different purpose. It has issues with double counting. By the way,
the Heron paper, if you read it, it just leaks every single problem in Storm. So if you're about to use Storm, just read the paper to see what you're getting into.
So
it's kind of hilarious.
There's double counting, there's state management, There's a bunch of things.
You can't really use a debugger with that, which as a developer, it's kind of like,
Yeah, we can talk about it offline if you want. But you can definitely go there if you want to go there. But you're going to run into issues that this architecture doesn't have.
Anyway, we are totally out of time, but Ted and I will still be outside for however many questions you're going to have. So thanks, everyone.